Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth. Hello and welcome to Physics with Beth and Beth. I'm Beth. We're on this AP Physics 1 review per request. We're doing these review videos. This is a free response question that I absolutely love. I don't know what that says about me, but I love this problem. It's just, whoever wrote this was genius. So way to go, AP board, because it's an old AP question. Well, not that old, but it's an AP question that's out there. Love this. And what we're going to do is we're going to be using lots of different units. Now, I am going to just explain what's going on, and as I'm explaining it, I'm going to tell you my thought process of how I would approach this problem and think about where do I even start, because that is half the battle on these physics problems. You have what I used to tell my students, this huge tool belt filled with all these equations in your equation tool belt, and which one do I pull out and when? That's always half the battle, right? So here's what's happening. I have a block 1, it's on a pendulum. So this is a pendulum, and block 1 swings down to this position right here. Okay, well, I'm seeing two things in my thought process. First of all, I see a change in height. All potential energy, because this thing's at rest, going to all kinetic energy, because we're going to call that top of the table 0 meters. So I see a conservation of mechanical energy. I also see that that is a pendulum that's moving in a circle. Now, it's not going all the way around, but it's still moving in a circular path. So that's centripetal force. That might be Newton's second law for centripetal force, but I got two equations there I can use for my equation tool belt. Then what happens is once one gets vertical, it hits block 2. Oh, that's a collision. That's conservation of momentum. All right, then when it hits 2 flies off, horizontal projectile. That's not at an angle. It's going to be a horizontal projectile and land on the floor at a distance 4L. And that tabletop is a height of 2L. Okay, so I'm seeing centripetal motion from the pendulum. I'm seeing conservation of mechanical energy from position 1 to position 2 of block 1. I'm seeing conservation of momentum with the collision. And then I'm seeing projectile motion with block 2, and then it's still not done. Block 1 swings back up to a final position up here. Again, I'm seeing conservation of mechanical energy because I'm seeing it's at rest. It was all kinetic, block 1 down here, and it's all potential at the top. Okay, they're going to ask you to derive a bunch of things. This would be probably like a quantitative, qualitative. We're not going to actually I'm not giving you numbers to have math and to have actual answers, but I'm going to be asking for several expressions. All right, we're going to get started with derived velocity at the bottom of the swing for block 1. This is block 1. Block 2 is just setting at rest on the table until it gets hit. Well, again, I said, hey, I'm seeing a change in height. When I see a change in height like that, I'm going to mechanical energy initial equals mechanical energy final. All right, and I've got all potential first, and I've got all kinetic at the end. So because it's completely vertical, I would call that tabletop 0 meters. My marker looks like it's starting to go out here. Let me try switching. So that's going to be mgh is my potential energy due to gravity. But they said, hey, block 1 is 3m and block 2 is m. So I'm going with 3mgh equals 1/2 3m v squared. All right, well, everybody brought 3m to the party. Woohoo! Cube party in the USA. I'm going to multiply by 2. I get 2gh equals v squared. I'm going to take the square root of that, and I get that my expression is the square root of 2gh. Now, h, though, they said only use the variables they gave you. They never gave me an h. So I'm like, oh, so what is this length? Well, the length of the string they tell you is L. So that means this is L. And then this is L. So actually H is L. So we're going to sub that in to make sure that we're consistent. Because all of these expressions, it says use only in the expression what we gave you, which is L, there's a theta, there's masses, and then constants, which would be little g. So now we have an expression for that. Second thing, it says, hey, give us a free body diagram on only block 1 and at where it's vertical. Where the string is vertical. So we're going to do a free body diagram on that block 1. Well, I have tension up. Okay, and you might want to do force of tension. And then down, of course, I've got force due to gravity, which is M1G. I'm going to put M1 because we have a block 1 and a block 2. Okay, so that's our free body diagram. That's the only forces we have when it's right here in this vertical position. So now it says, okay, derive tension when the string is vertical. Okay, this was moving in a circular, again, kind of walking you through my thought process. Okay, when I'm here, that was moving in a circle. So I'm going with Newton's second law for centripetal forces. Okay, I have tension, and really remember centripetal forces, center seeking or positive, and if they're opposite center seeking, they're negative. All right, well, center was this way because here's the center. So that means this direction is center. So that means force of tension is positive minus your force due to gravity is negative equals mass. And then they did not give me centripetal acceleration as one of my constants. So I'm like, oh, I need to sub in. I'm going to let the problem guide me. I just found velocity. All right, so I have an expression to fill in there that is just the constants they gave me. I'm going to let the problem guide me. I found velocity in part A, and now I'm at centripetal acceleration, and I know centripetal acceleration equals v squared over r. I bet I can use that in this. So I'm going to go ahead and sub in v squared over r. Okay, my force tension is what I'm looking for. So that's going to be mv squared over r plus, and for force due to gravity, remember, force due to gravity, I'll put it over here, is always mg. So I'm going to put mg. And by the way, this is the tension in that block 1. So that's block 1, block 1. Now I'm going to start filling in some numbers. And I might have to, we have force of tension equals M1 is 3M. V squared we know. V squared is 2GL. So I'm going to put in 2GL. And R, what is that R? Well, remember R is length. That radius of that circle that this block is moving in is the length of the string. That's L. Plus M1, block 1 is 3M times G. All right, now I'm going to have to move, running out of room. I'm going to move over here and then I'll erase it. So I'm going to clean that up. So my force and my tension, my L's cancel because I have 2GL. Let me rewrite that because you probably can't hardly see that. That was 3M, 2GL over L because this was V squared over R. V squared, we use 2GL. And because V was square root of 2GL. Boy, that's hard to say. And then V squared would be 2GL. R was L. And then we had plus 3mg. Okay, now all I'm going to do is my L's cancel. All right, and now I have my force of tension is 3 times 2 is 6 mg plus 3 mg. And you get that this thing equals 9 mg. OMG. Sorry, I had to do that. So that's 9 mg. Okay, now we're on part D. We're going to derive the time when block 2 leaves the table and lands on the floor. Well, when block 2 leaves the table and lands on the floor, that is horizontal projectile motion. And they want a time. Okay, I'm going to go with my y final position equals my y or vertical initial position plus my velocity initially in the y times time plus 1/2 my acceleration in the y times time squared. Now I've got all my little y subscripts to remind myself I'm talking about vertical here. I'm not, remember, we have to, the vertical direction and the horizontal direction are completely separate in projectile motion, right? What is happening in one direction is not necessarily what's happening, it's not what's happening in the other direction. Vertical versus horizontal. So I'm going to be in the vertical here. And I've got my final position in the y equals my initial position in the y plus my initial velocity in the y times time plus 1/2 my acceleration in the y versus time squared. Okay, now, because I needed to use one of the big three. Horizontally, if I look at my horizontal, I have no acceleration in the horizontal. So that direction is not going to do me any good. That's why I picked the vertical direction, if you kind of want to know my thought process. Because remember, acceleration in the x is just 0 because Earth pulls down, not horizontally. So that wasn't going to help me in solving for time with any of the big three. So I'm going vertical. My final position is 0. My initial position in the y, I start at 2L. So I'm at 2L, I'm just subbing that in. My initial velocity in the y is 0. And you're like, but you have initial velocity. You have to have initial velocity for it to shoot off the table. True, but that's initial velocity, look, in the x direction. It's not moving in the y at all. There's no angle here. It's strictly horizontal. So there's no initial velocity in the y. Plus 1/2 acceleration in the y t squared. I am going to subtract this 2L over. I have 1/2 acceleration in the y times squared. All right, this acceleration in the y is negative. Don't forget that. But anyway, we're going to multiply by 2. I get negative 4L equals acceleration in the y times t squared. Well, my acceleration in the y, if you remember, is just negative 9.81 meters per second squared. Or you could say a negative g is really what that is. Negative g, because they told me in this I could use constants and what they've given me. So that little g is a constant. I'm going to divide by a negative g, and that's going to give me 4lg, because my negatives are going to cancel, equals t squared. I'm going to take the square root of that, so I have 4lg square root equals my time. And that's going to be the answer for D. Okay, so now we're going to do part E. We are deriving the velocity that block 2 leaves the table with. Okay, again, I know I keep saying it, but I'm going to let the problem guide me. All right, we're going to have to figure out what this velocity is that it leaves the table with, but I just found the time, an expression for the time that it was in the air. All right, and it's a projectile motion, and it's a horizontal projectile motion. And I now know the time in the air. So I'm going to go with, hey, I know that x final equals x initial plus the velocity initial in the x times time plus 1/2 the acceleration in the x times squared. It's just the big three. However, I'm going to remember that I'm talking about the horizontal direction. That's why I've got all these x's in here. This is horizontal. And when you're talking about the horizontal direction in a projectile motion, your acceleration in the x is 0. You only have acceleration in the y, and it's negative 9.81 meters per second squared, which you can really use 10 on the AP exam, and it's easier. So this whole thing becomes 0. I start here, and I can make that starting line 0. So I can say my initial position is 0. So now I have x final equals that initial velocity in the x times time. And that's what they're asking for. Hey, what does that block leave with? What is its initial velocity in the x? And that's for block 2. All right. Well, we know that it travels. What's its final displacement? XF? It's 4L. They tell us that this length is 4L. This block 2 ends 4L away. So that's going to be 4L. My initial velocity in the x direction for that block number 2 is what they're asking for. And I just found an expression for my time. It's square root of 4L over g. Now I'm going to divide time over to get that initial, and I get 4, I'm going to write it over here, 4L divided by the square root of 4L over g. And that's going to equal my initial velocity in the x. And, or you could rewrite this to make it better. You could say 4L, and you could say the square root of G over 4L. Because you could, that's all on the denominator, so you could flip it and it could look like that. But anyway, you could clean it up like that or leave it like this. Okay, but that's what that initial velocity is. I'm probably going to leave it like this because I like this one better, looks cleaner. Anyway, so that's E. Now we're going to F. Derive the speed of block 1 just after it collides. That's going to be my big clue, collision. I'm going with conservation of momentum. Momentum before equals momentum final. Now I'm going to look at that collision. I'm going to look as block 1 on the string hits that block 2 at rest. Okay? And then that's going to be before. And then after collision, you still have block 1 is going to be moving. And that's what they want. What's that speed of block 1 after collision? And then block 2 gets shot off at this initial velocity. Initial for the projectile anyway. It's going to be really final in this. It's at rest, and then now it's got this velocity over here. And that's on block 2. All right, so I'm just going to figure it out. First of all, in initial, and remember, momentum is mass times velocity. Before, this is at rest, so no momentum. Only block 1 has momentum. And block 1 has a mass of 3m times its velocity right there when it's vertical. Oh, look, we found that right when it was vertical. We knew that velocity, right? So that velocity right when it's vertical swings at the bottom. Right before it hits is going to be the square root of 2GL. Okay, now final. I've got 2 things moving after the collision. I have block 1 moving, so that's going to be 3m times whatever that final velocity is after collision, and that's what we want. What's the speed of that block after it collides? That's what we're looking for, this V final of that block 1. All right, then after, we also have block 2 moving. Its mass is m, and look, let the problem guide you. We just found the velocity for what block 2 is right after the collision. It was at rest, and then right after the collision, it has this velocity in the x direction as it becomes a horizontal projectile motion. So that's going to be 4L times the square root of G over 4L. And we derived that through one of our UAMs. Okay, now I just have to clean this up and solve for final. All right, so I have 3mv square root of 2GL minus 4LM square root of G over 4L equals 3mv final for block 1, which is what we're looking for. Okay, everybody brought mass to the party. I'm loving that. And I am going to have a 3v square root of 2GL minus 4L square root of G over 4L divided by 3 equals V final 1. Let me just make sure that is correct. I knew there was something wrong here. I'm so sorry. Look at this. I replaced that velocity with the velocity equal to square root of 2GL. Sorry about that. I'm like, something is not right here. That's 3 to square root of 2GL minus 4L square root of G over 4L, and then all divided by 3 equals that V final. This is your final expression. Sorry about that extra little V. I forgot to, when I subbed it in, I forgot to take out the V. Okay, now for our last question, G. Derive expression for the maximum theta that the string makes with the vertical. And it says, hey, this time, besides what we've given you, you can also have velocity, which is the speed of block 1 after the collision. Because this is a very ugly expression to plug into yet another ugly expression. So they're going to let you just say, hey, speed of block 1 after collision is V. And you can leave that in your expression. So we're very excited about that. So here's what I'm looking at. they want maximum theta. So I had a collision. I knew the velocity, so I'm going to draw this out. I had a collision, so we're after the collision, and this is block 1, and it had this V after collision, which actually looks like this ugly thing, and then it rotates up on the pendulum to this position over here, okay? And that's a change in height, and it's at rest up here when it hits its max height, and it's all kinetic energy down here. So I'm like, oh, I know, I'm using conservation of mechanical energy because I see a change in height. So I have mechanical energy before equals mechanical energy after, or final. Before really means after collision, and then final really means at max height on the pendulum, because we are only talking about block 1 here. This is just block 1 that they're wanting, that's related to that theta, because it's only block 1 that's on the pendulum. 2 is already shot off the table on a horizontal projectile. Okay, so we have all kinetic energy here. We're going to all potential energy here. Kinetic energy is 1/2. And remember, this is block 1. It has a mass of 3m, so it's 3m. And they said that, hey, you can use velocity for the speed of the block 1 after collision. So that's 1/2 m mass 1, which is 3m v squared. Now, mgh is going to be 3m because mgh, the m1 is 3m, g, and then I have h. Okay, so what they want is that theta. I'm going to have to figure out how to get theta in this equation. It's not in this equation yet, but hopefully we can remember this from before. This is theta, this is the length of the string, and this is the length of the string, okay? Because the string didn't change lengths when it was swinging. And if I go dinky, dinky, dinky over here, this little piece right here, that is L cosine theta. All right, that is L cosine theta. I don't have any other colored markers over here, but let me write it. That's L cosine theta. This little piece right here. Why? Because this is theta, the hypotenuse is L, so this side is adjacent to that theta. That's L cosine theta. Now, if I want my height change, this is my height change right here. From this bottom of the block to where, or the middle of the block, really, I should have drawn it out to the middle of the block here. That's height. That's how high it was lifted for its potential energy off the floor. Well, this whole thing is L, and this little piece is L cosine theta, so H equals L minus L cosine theta. The whole length of the string minus this little piece, L cosine theta, and that equals H. Now I have something to plug in here to get this. So I'm going to do 3/2. Oh, look, everybody brought 3m to the party. So yay, cube party in the USA, cancel that out. And I have 1/2 v squared equals g, and that's L minus L cosine theta. Now I'm going to try to clean this up a little bit to get, ooh, that didn't work. I'm going to clean this up a little bit so that I can get, still not working very well. Good thing we're at the end of AP Physics 1 curriculum. We need a new eraser. All right, but here we go. I'm going to divide by g. So I have v squared over 2g equals L minus L cosine theta. I'm going to add, let's see, I'm going to add L cosine theta over to both sides. I'm going to subtract v squared over 2g to both sides, just to get my negative out in front of the variable that I'm looking for. Now I'm going to divide by L, both sides, and I get cosine theta equals L minus v squared over 2g divided by L. You can actually clean that up, and I'm going to clean that up over here. And theta, I am really running out of room on these free response questions. I have theta is going to be cosine inverse. That's how you're going to write that, because I got to get theta by itself. L divided by L is just 1. And then I have v squared over 2gl. The L got divided by both of these expressions. I divided L. Well, L divided by L is 1. And then I have v squared over 2gl now. And that is my expression for theta. Okay, thank you for sticking with me on this video. It was a doozy, but I really wanted you to see the thought process on a very complicated free response question on how don't ever give up. Any point can be the difference between a 3 and a 4. You never know. So don't give up, but look, if you see a change in height, conservation of mechanical energy. You see a collision, conservation of momentum. You see a projectile problem, the big 3. Okay, you see something moving in a circle, centripetal motion, Newton's second law. So hopefully that helps. That was very complicated, but remember, you can do this. Every point counts. And you're not expected to get every point on the free response questions to get a 5 even. All right, so hang in there. You've got this. You can do it. Thank you for watching and happy physicsing.